Okay, hello everybody. So this is the week 5 hybrid supplement. The goal for today is to finish up PowerPoint number 2 from chapter 4 that we started in class on the multiplication rule and conditional probability, and then start and complete PowerPoint number 3 that I handed out in class we haven't gotten to yet, dealing with counting. And then that will wrap up chapter 4. And this coming Tuesday, we will start chapter 5, discrete probability distributions. So I would recommend that you look through the first section or two of chapter 5 just to kind of get acclimated with what we're going to be talking about next. Okay, so let me switch my screen share here and then we will get started. Okay, hey everybody, this is the supplement to finish up chapter 4. So the plan for today is to finish up the second PowerPoint in chapter 4 and also start and finish the third PowerPoint on the section on counting. And that'll wrap up chapter 4. And then this coming Tuesday, we will start on chapter 5. So we'll start in the 5.1 on Tuesday. Okay, so we had in our last class gotten to the section on conditional probability. And we mentioned that by rearranging our multiplication rule for dependent events, we can solve for probability of B given A, the conditional probability that event B occurs, given that we know that A has occurred. And we see that that will be equal to probability of A and B over probability of A. We talked about this coin flipping example in class, and this is about where we left off. So the next problem, the next example of conditional probability is this one. The probability of parking in a no parking zone and getting a parking ticket is 6%. So let's suppose that we're a student at a busy campus like Pitt or something, and we're commuting there. So we know that kind of on average about 6% of the time we get a ticket. So 6% of the days that we go into school, we get a parking ticket that day or something like that. So one way to kind of think about this probability is on 100 days when we leave the house and we don't know what the parking situation is going to be like, we would estimate that of the 100 days like that, about 6 of them we would get a ticket, and about 94 of those we would not get a ticket. Some days we would park legally and not get a ticket. Some days we might park illegally and get lucky and not get a ticket. We also are told that the probability that you can't find a parking space and need to park in a no parking zone, so the probability that you risk getting a ticket, is 20%. So 1 day out of 5, you know that historically you get to campus and there is nowhere to park and you're in a hurry and need to get to class, so you park somewhere illegally and hope that you don't get a ticket. That happens 20% of the time. And the question is, given that you parked in a no parking zone today, what's the probability you'll get a ticket? So we want to find probability of ticket given that we parked in a no parking zone. And this is the probability of getting a ticket and parking in a no parking zone over probability of parking in a no parking zone. Or this is 6% over 20% or 30%. So there's a couple different ways to think about this information, but I think the maybe the most natural way to think about it is when we left our house this morning, before we knew anything about the situation on campus, whether it was a busy day or not, whether there's some big event going on or construction that's blocking a whole bunch of spaces or something like that. When we left this morning, the probability of a ticket was 6%, 0.06. When we get to the campus and we realize that for some reason we can't find parking and we need to park in a no parking zone, that's additional information. I think it's pretty clear under that additional information that we chose to park illegally today, our probability of getting a ticket should increase, given that we've parked in a no parking zone. But how much should it increase? Well, we can look at a way to evaluate that increase systematically. It should increase from 6% to 30%. So once I get on campus, realize that parking is tough today, I need to park in a no parking zone to make it to my exam on time or something. My risk of getting a ticket that day has gone from 6% up to 30%. And of course, it's no mistake that 30% is 5 times 6%. That's what this ratio of 0.2 here in the denominator is doing. 0.2 is 1/5. So when we invert that, that's multiplied by 5. So the way that I kind of just explained it is somewhat of a Bayesian or a subjective probability point of view, where as we accumulate more information about the world, more information about some particular system, namely that we have new information that we had to park in a no parking zone today, how do we update our probability in light of that new information? This will be a very common theme in the section on Bayes' theorem at the end of chapter 5. And one last example, dealing with bringing a pharmaceutical drug to market. So a couple notes on this example. The research I did into these numbers is from nearly 10 years ago at this point. So I looked into a lot of different peer-reviewed articles and things where people were looking at what does it cost to bring a drug to market. Now, of course, most pharmaceutical companies are privately held, or I mean, maybe publicly traded, but they're not government entities. They're not spilling all of their secrets, so to speak. They keep their trade secrets internal. So this can be kind of a difficult number to obtain. So looking around at some different publications, at some different estimates that folks had done, and also simplifying the process of going through research and clinical trials. And so I came up with this model. I think this model does a reasonable job at getting at the heart of the problem, but I had to fill in a few gaps here and there, make a few inferences. But the number that I kind of end up with at the end is on the conservative side of what it would have cost on average about 10 years or so ago to bring a drug to market. So, so with all of those caveats, let's go through this problem. So suppose that we are a pharmaceutical company. We want to develop a new drug. We want to bring a new drug to market. And we're going to think of an idea, a potential drug, as having to go through 2 stages successfully to make it to the market, to be able to be sold to the public and for us to make a profit off of it. The first stage is that the drug must go through basic science or preclinical trials. So these are, we develop the drug, we manufacture it, we, put it in a lab, smear it on a petri dish of bacteria or something, see if it kills the bacteria, those kind of things. Maybe, try some mouse models, something like that. If it doesn't work in a lab setting where everything is very controlled, it's quite unlikely to work in a complex environment like inside the human body. So the drug has to pass these preclinical trials. It has to pass the lab tests in order to move on to a clinical trial where we're going to invest an awful lot of money into trying to actually bring the drug to market and prove that it works in humans and it's effective and doesn't harm them and all of those kind of things. So if it passes the preclinical stage, it moves on to clinical trials. And then if it passes the clinical trials, it'll be marketed to the public. So of the drugs that, let's say of the ideas that are brought into the lab to see if they can become reasonable drugs, 2% of them pass the preclinical trials. 2% of them, these kind of ideas that some scientist has, 2% work in the lab. If an idea works in the lab and kind of has the potential to become a marketable drug, then it moves on to clinical trials. And once it hits a clinical trial, there's a 25% chance it will pass through the clinical trial successfully and make it to the market. So again, an overly simplified approach. There are different, different stages to clinical trials. There's probably different, stages, at least philosophically, to lab work, whether you're doing just basic science research or working in animal models, but we're simplifying this down. So let's try to find the overall probability that a drug makes it to market and try to answer the question that on average, how many drugs or kind of how many initial ideas need to go through this process to get one successfully to market. So we can set up a tree diagram. We see that of the ideas here on the left, they first have to go through preclinical trials through the lab work, and that lab work can either be a success or a failure. 2% of the ideas succeed in the lab, so 1 out of 50 is the probability of preclinical success, and 49 out of 50 is the probability of preclinical failure. Now here I've kind of truncated the tree diagram because we know that if we fail the preclinical trial, then the drug is not marketable. We don't do a clinical trial after that. But if I have a preclinical success, if the drug works in the lab, we need to run a clinical trial. We need to make sure things like that it will actually still work in a more complex environment like the human body. We have to make sure that, the side effects aren't so terrible that the people can't tolerate it, things like that. So in the clinical trial, we could either have a success or a failure. So we could ask, what's the probability of a clinical trial success given preclinical success? And that's 25%. Given that we passed the lab work successfully, 25% of chance of succeeding in the clinical trial, and 75% chance of failing to succeed in the clinical trial. And the only way that we get a marketable drug is if we go up, so to speak, if we succeed in both the preclinical and the clinical trial. We can find the probability of reaching each of these leaves of the tree on the right here by multiplying the probabilities along their path. So 1/50th times 25% times 1/4 is 1 in 200 chance that we get a marketable drug from an initial idea. 1 in 50 times 3/4 is 3 in 200 chance that we end up with a non-marketable drug after going through lab work and clinical trial. And 196 out of 200, which is just 49 out of 50, changed into the same denominator that we have up above. So 196 out of 200 chance that we fail in the lab, and then we just don't do anything with the clinical trial. So if on average we have a 1 in 200 chance of a given idea ending up becoming a marketable drug, I think we can pretty clearly see that on average we need to have 200 such ideas to run through this process to get one marketable drug. Now let's look at costs. So the costs for these things are quite high, right? These aren't cost numbers that we're used to seeing in our household budget or something like that. The equipment that they're using is extremely expensive. They have salaries for all kinds of PhD chemists and people to pay. So I've estimated that, again, this is where some of the fudging comes in, but I've used these numbers to kind of make the end number work out relatively correct, and some of the other probabilities and so on to work out roughly the way that they line up in the research. So let's say that preclinical trials cost on average $1 million. So the lab work to decide whether an idea is likely to work well enough to become a drug or not costs on average $1 million. So this will be the time for the lab techs, the time for the researchers, the cost of all of the lab equipment and reagents and chemicals, and producing any chemicals that need to be produced, etc. And let's suppose that clinical trials cost on average $150 million. Again, clinical trial is going to enroll hundreds or thousands of patients. They're going to have cooperation between lots of large health systems. There's tons of research, tons of production. Clinical trials are extremely expensive. So under these assumptions here, what's the cost to bring one drug to market on average? So on average, out of 200 trials, we'll have 196 fail in preclinical trials in the lab stage at, let's say, an average investment of $1 million each. Now, again, we're talking average investment here, so some they might realize really soon that this isn't likely to work and maybe cut their losses, but others they might, have a long extended lab work stage where things seem promising, and then at the last minute they realize that okay, there's some serious problem here. So this is kind of an average number, but 196 failing in the lab work stage at a cost of $1 million each on average will give us 196 million. Similar with clinical trials, sometimes we'll know earlier and cut our losses. Sometimes we'll get all the way to the last stage and it'll fail there. So 3 drugs will make it successfully through the lab stage but fail in clinical trials. They'll cost 151 million each. So 150 for the clinical trial on average and 1 million on average for the preclinical work. So that's 453 million. And one will make it to the market at a cost of, say, 151 million. The total cash outlay, and again, this was about 10 years ago, and a conservative estimate is around $800 million. So why does it cost so much to bring a drug to market? This 151 is what we actually spent on the idea to get it to the point where it's a marketable drug. Oh, but that success also has to pay for all of the R&D expense, all of the research and development expense, or in other words, it has to pay for all of the ideas that failed, that went partway through a clinical trial and ended up not being a marketable drug, or the tons of ideas that somebody's trying something in a lab and it just doesn't even work in the lab. So the success has to pay for all the failures. Or this one branch of the tree that goes up is the only branch that really generates revenue, and it has to pay for the other branches. And again, this is a simplified model. There are some examples, say like maybe some drugs are a little too dangerous to use in humans, but maybe they can turn it into a veterinary drug or something and use it in animals successfully, or maybe the animals don't experience the same side effects. So, right, there's much more complexity to this in real life, but anyway, I think this is an interesting kind of tree diagram and conditional probability problem, and I think the tree diagram sheds a little bit more light on pharmaceuticals, which is kind of a topic of interest today in a lot of spaces. Okay, so now we're going to move on to the third PowerPoint in Chapter 4, Probability. And this PowerPoint deals with counting. Let me resize my window here. So really quickly, why are we going through a whole section on counting? Well, we know that the probability of an event from classical probability, provided that all outcomes are equally likely, is the number of outcomes in the event over the number of outcomes in the sample space. And so far, we've had pretty simple sample spaces. For instance, the roll of a 6-sided die, 1, 2, 3, 4, 5, 6. So it's pretty easy, obviously, to count the number of outcomes in the sample space. There are just 6 of them. And if we had an event like, say, rolling an odd number, it's pretty easily to just brute force count all of the odd numbers. There's 3 odd numbers here. So our probability of rolling an odd number, 3 out of 6, 1/2. We saw slightly more complex sample spaces and events, like we might roll 2 dice, and we might have a first roll and a second roll, and that gave us a grid of size 6 by 6, or 36 distinct, equally likely outcomes. But we could imagine more complicated sample spaces. For instance, what if we wanted to roll 3 dice or 4 dice, or what if we wanted to flip a coin 10 times? we might be able to extrapolate from, say, the multiplication rule or something like that. Maybe what the size of the sample space is. For instance, we might say that for flipping a coin 10 times, the probability of getting 10 heads in a row is 1/2 to the 10th by the multiplication rule. Well, that's 1 to the 10th over 2 to the 10th. And I know there's only one sequence that yields all heads, so maybe that kind of suggests that the size of the sample space is 2 to the 10. But we could imagine an event in something like that, like something like the probability of 4 heads and 10 flips. Maybe we can kind of work out the size of the sample space, but what's the number of outcomes in this event? This is going to be a very challenging thing to count, right? There's going to be a lot of ways, a lot of sequences of 10 heads and tails that have 4 heads and 6 tails in them. I really don't want to go through and count all of them to try to brute force it or kind of work my way through all of them. It's going to be very tedious, and frankly, it's going to be such a big problem. I'm probably going to make a mistake somewhere. So I would like a method, I would like a formula that would help me count events like this. And we have a few formulas, and different formulas apply in different situations. And that's the goal of this counting section. Okay. So our first rule, the fundamental counting rule, we'll see that we have something like 4 rules. We might think of 2 of the rules as kind of really being different points of view on the same rule, but we have something like 3 or 4 rules. And the most basic rule is the fundamental counting rule. This is really the rule that all of the others are kind of based on. So suppose that a probability experiment consists of n ordered trials. So we have a first trial, a second trial, a third trial, maybe something like rolling a die a few times or rolling a few different dice in sequence, something like that. Each of which, each trial has k sub I possible distinct outcomes. So maybe the first die that I roll is a 6-sided die, so there are 6 outcomes for that first trial. And maybe the second die I roll happens to be a 20-sided die, so there are 20 outcomes for that second trial, and so on. Then the total number of unique sequences of outcomes is the product of those ki's. And sometimes I use the terminology of slots to fill in versus items with which I can fill in each of those slots. So maybe there's K1 items that could be used to fill in the first slot. Say the die roll numbers 1 through 6. Maybe K2 items that could be used to fill in the second slot, and so on. And the number of outcomes is the product of all of these ki's. So let's look at a couple examples. So for instance, how many possible outcomes, unique sequences, are there in 4 flips of a coin? Well, each of the 4 trials, each of the 4 slots, has 2 different possibilities, heads or tails. So K1 is 2, K2 is 2, K3 is 2, K4 is 2. And the total number of distinct sequences of heads and tails is 2 to the 4th, or 16. Now, in this case, just as an exercise, we can enumerate all the outcomes. This isn't a terrible number of outcomes to enumerate, so let's write them out, the sample space. And I've kind of separated them here into, the first line has 4 heads, then 3 heads, 2 heads, 1 heads, 0 heads. So I see, of course, there's only one outcome where I get all heads. That's heads, 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 heads. Now, when I get 3 heads, I can think of that as just having 1 tails, and then I have to decide where to put the tails. I can put it last, second to last, second from the front, or in the front. So there are 4 outcomes that have 1 tails. When I have 2 heads, these are a little harder to count, but I can start by, say, putting both heads at the front, and then taking the second heads, the kind of right-hand heads, moving it 1 to the right. I can then move the one at the left over to the right to make tails, heads, heads, tails. I can split them apart. I can think of a couple of different ways of doing this. If I think in this direction, in the sequence that I've outlined here, it's a little harder to see what's going on. If I think in terms of the tails, I notice there's a lot of symmetry to this problem, right? If I have a line where I have two heads in all of the outcomes, that's the same as having two tails on four flips. If I think of the tails instead, things might make a little more sense. I might see the structure a little better here. I can start with my two tails at the end, move the leftmost tail one to the left, move it one further to the left, and then I've kind of run out of room moving the leftmost tail to the left, so I kind of bump the rightmost tail one to the left, move the leftmost tail back over, move it one to the left again, and then I've run out of room on the leftmost tail. So again, I take the rightmost tail, move it one to the left, and that finishes off my two tails and two heads. So one really important idea in some of these counting rules and some of these probability questions is to realize that when there's symmetry in a problem, a lot of times we can make use of it. So the way that I had these written here was really focusing more on the tails and going through an ordered, structured way of going through the tails rather than the heads. Now, you could have, of course, done this with the heads as well, and you'd have gotten a slightly different sequence of 6 here, but it would have been the same sample space. So again, if I come down here and I say, what are the outcomes that have 3 tails? Figuring out how to put 3 tails into 4 slots might be a little cumbersome. I could put the 3 all the way to the right, or I could, start moving these tails around, but I could also realize that saying 3 tails is the same as saying there's 1 head, and then it's much clearer. Well, if I have to put 1 head in 4 slots, I can put it in the first slot, the second, the third, or the fourth, and those are the only choices, right? So sometimes a slight shift in perspective in these kinds of problems really makes a huge difference into how easy the problem is. And then lastly, no heads, all tails, there's 1 outcome there. So note that if I were to say something, if I were to describe my outcomes as something like 0 heads, 1 head, 2 heads, 3 heads, 4 heads, these would not be equally likely, right? We see that 2 heads has kind of 6 outcomes that contribute to it, where say 0 heads has only 1 outcome contributing to it. So these events over here would not be equally likely, but these might be events that we're interested in, and these are some of the types of events that our counting rules are going to help us with. Okay, how many standard Pennsylvania license plates are there? A standard Pennsylvania license plate has 3 letters followed by 4 numbers. And note that in a situation like this, I can reuse letters, right? AAA1111 is a valid license plate. It's not like once I've assigned A, I can't assign it to any of the other slots. So I have 26 choices for the first slot, 26 and 26 for the second and the third, and then the numbers 0 through 9, so 10, 10, 10, 10. And this is where I get this 26 cubed times 10 to the 4th, or around 176 million. Note also that in the fundamental counting rule, order matters, right? Different orderings represent different outcomes. These are ordered trials, so to speak. In other words, ABC 1, 2, 3, 4 is a different outcome, a different license plate than CBA 4, 3, 2, 1. So if we were interested in passwords, maybe we're interested in for a certain password structure, what are the number of possible passwords in that structure? And why might we be concerned with this? Well, if somebody was trying to brute force their way into our account, they could just try a whole bunch of passwords, and the smaller the password space is, the more likely it is that they're just going to guess our password. For a stupidly trivial example, if you imagine that everybody's password was just either 0 or 1, so a 1 bit of information, it would be quite easy to guess somebody's password, right? You type in 0, you try it, and if that doesn't work, you type in 1, and you're going to get in within 2 tries. So we would like a password space to be quite large so that even if somebody had programmed a computer to kind of automatically try tons and tons of passwords, it's still going to be hard for them to get into our account. So if there are 8 slots, each of which can contain any lowercase letter that are allowed, how many passwords are there? So 8-character passwords using only lowercase letters, 26 choices for each slot. 8 slots is about 2 times 10 to the 11th. So if I have 8 slots, with 26 allowable characters each, this gives me about 2 times 10 to the 11th possible passwords. Maybe I look at this and I say, well, I mean, that's a lot of passwords, but computers can also do things very fast. Maybe I think that this is not quite secure enough. I would like a stronger password. So what could I do? Instead of just using these 26 characters, these 26 lowercase letters, I could maybe expand the character set that I can use. I can use maybe lowercase or uppercase letters, numbers from 0 to 9, or any of, say, 10 special characters, exclamation point, @, things like that. So I still have 8 slots to fill in. But now I have 72 items that can be used to fill in each slot. The 26 lowercase letters, the 26 uppercase for 52 letters, and then 10 and 10 for the numbers and the characters. So this gives me 7 times 10 to the 14th different passwords. So I've increased by a little more than a factor of 1,000. Going from here to here, I have around 1,000 times as many passwords. So for somebody to brute force their way in would take, say, on average, about 1,000 times as long. If it, was going to take them 1 day to break into my 8-character lowercase letter password, it'll take them 1,000 days to break into my 8-character more complicated password. Now, what if instead we had increased the number of slots, the number of characters, from 8 to 10, but kept lowercase? So we're still only using lowercase letters, but now there's 10 slots instead of 8. So if our password is 2 characters longer, even still using lowercase, we end up with 26 to the 10th power, or 10 to the 14th, in the same order of magnitude as our 8-character password with the much larger choice for items to fill in each slot. So kind of the moral of the story here is that increasing the number of slots increases the number of outcomes or the number of unique sequences much faster than increasing the number of items that can go into each slot. Increasing the number of items increases the base. So this is like 26 to the 10th. Increasing the number of items that can go into each slot affects the base, where increasing the number of slots affects the power. And we know that increasing powers, that's an exponential growth that grows much faster than polynomial growth, which is when we increase the base. Okay, so another example. So consider the human genome, and let's just think of all of the chromosomes kind of lined up, just head to tail with one another and straightened out so that they're not in their helix form anymore. And we can think of the genome as just kind of a long ladder like this. And there's a coding strand that consists of A's, T's, C's, and G's, 4 different nucleotide bases. And each nucleotide can be A, C, T, or G. And how long is the genome if we stretch it out like this? It's about 3 billion bases long, or 3 billion base pairs long. So what do I have here? I have 3 billion slots, each of which can be filled in with one of 4 items. So how many possible sequences are there the length of the human genome? Well, there's 4 to the power, the number of items to the power, the number of slots. Or as I say over here, this is, if we say 4 cubed is, something like 10 on this scale, 10 to the power of a billion. So a one with, a billion zeros or something after it. This is a couple of gigabytes of data stored in the nucleus of each and every one of our cells. And I don't know, I think that's kind of amazing that each and every one of our cells stores a couple of gigabytes of data. And we have something like 10 trillion cells in our body. Maybe I shouldn't say each and every one of our cells. Some of our cells don't have nuclei, and some of them have half this much data, but the overwhelming majority of our cells. If you like brush your hand against your arm or something, the number of cells that you've sloughed off of your arm is probably, using up more storage than is in your hard drive or something crazy. Okay, so moving on to the next idea, we're going to build off of the fundamental counting rule. We have this famous problem, the traveling salesman problem, famous problem in computer science, also in statistics. Suppose that a salesman needs to travel to 10 different US cities to meet with clients. So we're thinking maybe the kind of old days salesman, the 1950s, 60s, something like that, where they actually had to travel, fly or drive to different cities to meet with clients. And the salesman would like to choose the best itinerary for his needs and in some context, maybe the lowest cost or the shortest travel time, something like that. So the salesman would like to take each possible itinerary, review it, see what the cost would be, and then pick the one with the lowest cost. How many itineraries does the salesman have to review in order to find the best one? So what do we have? We have 10 cities, and we have 10 slots. So he has 10 slots on his itinerary, and these could be filled in with 10 cities, right? Maybe LA, New York, Pittsburgh, Cleveland, Wheeling, etc. But note a couple of things. Note that number one, the itineraries are such that order matters. So in other words, flying from New York to LA to Cleveland to, Portland to whatever, Wheeling to Seattle, we would consider that a very different itinerary than saying, whatever, Pittsburgh, New York, Wheeling, Cleveland, Seattle, LA, right? We think that would probably be a much more efficient one. So the order definitely matters here. So different orderings represent different itineraries. But also note that unlike the previous couple examples, here we're choosing without replacement. If we choose to travel to LA for our first stop, we're not going to travel there again on our 7th stop. We've already visited that client. So I have 10 ways to assign a city to my first slot here. But once I've assigned a city, once I say put LA in my first slot, I can't use it again for the second slot. So then the second slot has 9 cities remaining that can be chosen for the second slot. If I put LA in the first slot and Wheeling in the second slot, I can't choose either of those for the third slot. I have 8 remaining for the third slot, and so on. Down to 3 for the third to last slot, 2 for the second to last slot. In the last slot, I've already used up 9 of my 10 cities. There's only one left that just gets one choice for that last slot. So I see my number of itineraries. My number of itineraries is 10 times 9 times 8, all the way down to 3 times 2 times 1. And this is about 3.6 million. So probably not feasible for our salesmen, especially in the 1950s or so, to evaluate each one of these to see their cost and then to pick the one with the lowest cost. Our salesman would have to use some kind of heuristic, maybe come up with a few different decent candidate routes, and then actually evaluate those. So for just 10 cities, there's 3.6 million different itineraries. But this number grows incredibly fast. If we had 11 cities, then it would be 11 times this amount. So we'd be up to 33 or, maybe 40 or so million, something like that. This number grows very, very fast. Imagine something like FedEx who has to figure out how to deliver, I don't know, say 10,000 packages or something, or maybe even more than that, to folks in Pittsburgh every day. Right. I mean, there's an enormous number of different possible itineraries for something like that. They're going to have to use a lot of heuristics and a lot of good computer science and logistics to figure out good routing for all of those packages. So we might notice that we could type in 10 times 9 times 8 and so on into the calculator, but that's pretty tedious. And certainly if we had 30 cities, we really wouldn't want to type these all in. So we have an operator called the factorial operator that does this for us. So 10 times 9 times 8 times 7 and so on. If we have a positive integer and we take the factorial of that integer, so if we compute 10 factorial, that's the product of that positive integer with all other positive integers less than it. Our calculator has this built into it. So in the math menu over here, the top left is second and then alpha and then math. If we go to the math menu, we notice across the top there are 4 submenus: math, number, complex, and probability. We're going to go over to the probability submenu. And then we note line 4 here. We're going to navigate down to line 4. That's our factorial operator. If we hit enter, it puts a factorial in for us, and it has this answer there, but that's just because I hadn't typed anything in. So if I want to compute 10 factorial, I type in 10, and then I navigate to that factorial operator, math, go to the right to the probability menu, go down to the factorial operator, then hit enter. We have 10 factorial entered. Now we can hit enter again, and that's our 3.6 million answer that we had before. Something kind of interesting to note, it's a very helpful property of factorials, is that 10 factorial, if I pop this 10 off the front, then what am I left with? I'm left with 9 multiplied by all other positive integers less than 9. So I could think of this as 10 times 9 factorial. Or I could do that again. This is, 10 times 9 times 8 factorial. I can pop some of these leading factors off of a factorial, and I'm still left with something that can be nicely concatenated under a factorial. So this is a recursive idea. Those of you who have taken programming and things before, you might have actually programmed a factorial function as a recursion. Now something, so we can say as a general rule, n factorial equals n times n minus 1 factorial for n a positive integer. But then to define this recursion properly, we need a base case. And you might say, well, let's just take 1 factorial equals 1 and make this a positive integer bigger than or equal to 2. I suppose we could do that. We're actually going to see it's going to be much nicer to actually define 0 factorial to be 1. This might seem like a very strange thing when I said the idea of a factorial is to take a positive integer, multiply by all other positive integers less than it. But there's a couple perspectives in which this makes sense. One is that some of our future rules will just we'll be able to avoid a bunch of special cases by allowing 0 factorial equals 1. That actually kind of even makes sense in our factorial rule. If our salesman had 0 cities to visit, well, how many itineraries are there to just, sit on your couch and not go anywhere? Well, there's, I guess, only one, right? There's, You just have to not go anywhere. So in that sense, the 0 factorial equals 1 kind of makes sense. There's also a deeper reason why this makes sense, and it's related to something called the gamma function. We're not really going to get into that, but there is a somewhat deeper reason why 0 factorial equals 1, does also make sense. And this is just a little exercise like I kind of did up here where we could break apart our factorials. We can break our factorial using the recursion down into the other definition. So the general factorial rule is when we have n distinct items to be allocated to n slots, where order matters, in other words, where a different ordering represents a different outcome, then the number of unique outcomes is n factorial. So another example, reshufflings of a deck of cards. So consider a standard deck of 52 cards, and we want to reshuffle, we want to shuffle them very well, right? So like think of like throwing them up in the air, they go everywhere and then collect them back together, very nicely shuffled. How many such reshufflings are there? Well, we can think of there being 52 slots. I have 52 ways to assign a card to the first slot. Each of the cards is unique. 51 for the next, 50 for the next, so on to 3 times 2 times 1. So there are 52 factorial different reshufflings. How many is that? Let's check. So I could do 52 and then factorial. I want to go math. I could go all the way to the right to get to the probability menu. I could also just go left 1 and then wraps around. So I'll do that. And I could navigate down to 4 and hit enter, or I could just hit the button 4. If you want to do it the long way, no problem. But you can just go left 4. That will also enter a factorial. It's a little quicker. And I see that I have this kind of strange result. I have 8 point something, E67. That E means times 10 to the power. So this is 8 times 10 to the power 67. Again, this is an enormous number. The physicists estimate that there are something like 10 to the 80th particles, like electrons and things in the entire universe. So you can imagine 10 to the 67 is getting up to about that size. And I kind of did the math on this one time a while ago. And if you imagine that something like every person who has ever lived in history or is currently alive, if they all lived 100 years and they all did nothing their whole life but reshuffle cards, and they could reshuffle it like 1 shuffling per second. I forget if I did per second or per minute or something like that, but like the chance of any 2 people ever having at some point gotten the same shuffling of cards is like absurdly small. So I mean, this is an extraordinarily large number of reshufflings of a deck of cards. Now you will hear every once in a while there will be a group of people playing bridge or something and some really crazy thing happens where I don't know, like they deal the cards to the 4 people and like each of the 4 people only gets like a single suit, like one person gets only clubs and the other person gets only spades or something. Most of the time, if you actually dig into what happened, I mean, some people I suppose could just be lying to get in the news or something, but most of the time you can kind of make sense of it by saying, okay, well, when people actually shuffle cards, we might start with a new deck, which has obviously a non-random ordering. It has the random ordering of basically every new deck out there. And then we shuffle them, but, we kind of think that by shuffling them, we're randomizing them, but really, if we do a riffle shuffle, we tend to kind of roughly kind of interleave one from the left, one from the right. And then every once in a while that gets jumbled up a little bit. So it's maybe, 1 or 2 shufflings doesn't randomize the deck as much as we might think. And so it's more likely that those kind of situations happen from starting from a new deck, the predictable nature of how people shuffle, and then that led to something that seemed very unlikely to happen, but you could easily explain it away with starting from a new deck, and then human behavior. But if somebody had picked up a deck of cards that they had used 20 times already in different games and then done this, that would be much more impressive. Or if they had, riffle shuffled them, say 8 or 10 times, at that point they're pretty well randomized, and that would be much more impressive if something like that were to happen in a situation like that. So again, revisiting the traveling salesman, as I mentioned, the traveling salesman has 10 factorial different itineraries to look through. As kind of a side note, n factorial kind of looks like n to the power n. It grows faster than even an exponential function. So we have an n in the exponent, but also an n in the base. So this grows extremely fast. It grows faster than an exponential function. There aren't a lot of things that grow as fast or faster than factorials. So if we even went up to, say, 20 factorial, if our salesman would do second enter to bring up the previous entry, and then if our salesman had 20 cities to visit instead, all of a sudden, instead of 3.6 million itineraries, he's got 2 times 10 to the 18th itineraries. As an aside, if we do on the calculator 69 factorial, we see that we get about 10 to the 98th. And if we try to do 70 factorial, we get an overflow error. 70 factorial is too big for our calculator to do, or any other input bigger than 70, at least for the TI-83. Now this could change depending on what calculator you have. Some more modern calculators might be able to do higher numbers factorial. But for the 83, 69 factorial is the highest factorial that it can do without overflowing. This actually becomes a bit of an important point later on. We'll see that in some more complex situations, we have a lot of cancellation in the numerator and denominator. If we try to explicitly write out a formula with factorials, the calculator might try to calculate it one way and overflow, but maybe if we enter it in the calculator a slightly different way, the calculator can take advantage of that massive cancellation and not overflow. So this will be an important point later on, that factorials grow very quickly, and inputting large number factorial into the calculator can easily make it overflow. Okay, so let's consider a lazy traveling salesman. So this salesman also was told by his boss to go to 10 different cities and meet with 10 different clients. But he's going to only travel to 6 of these cities and whatever, spend the rest of the time on a beach in Florida or something. How many itineraries does this salesman have to choose from? So this salesman has 6 slots to fill in rather than 10. But he still has 10 different cities to choose from. So still 10 different cities could take up the first slot, then 9, 8, 7, 6, 5. So I see the number of itineraries is 10 times 9 times 8 times 7 times 6 times 5. And again, I guess I could type this into the calculator, but we could imagine, having 30 cities to visit and picking from 15 of them. And we wouldn't want to type that in. So let's try to come up with a formula that we can write a little more concisely. Something that I notice here is 10, 9, 8, 7, 6, 5. Like, this is a start of a factorial. If only I had a few extra factors, it would kind of complete the factorial. This feels to me like completing the square from algebra. So this would be super nice if it was this instead of stopping at 5, because then I could just write 10 factorial. Now I can put these factors in here. That's not a problem as long as I take them out. But nicely enough, on the bottom, I just end up with 4 times all of the other positive integers less than it. In other words, I end up with 4 factorial on the bottom. So if I did 10 factorial divided by 4 factorial, I get 151,200. I could also have done 10 times, wrong screen. There we go. I could have done 10 times 9 times 8 times 7 times 6 times 5. That would give me the same answer. Now, it turns out this kind of structure comes up enough that we have a name for it. We call it a permutation. And we have a formula for it. I note that the 4 factorial on the bottom is related to the 10 cities, the 10 items I have to allocate, versus the 6 slots. It's 10 minus 6 factorial. So 10 factorial over 10 minus 6 factorial. We give that the name 10p6. And we would just say it that way, 10p6. If we go into our math menu, go to the probability menu, we note this NPR operator here in line 2. This NPR operator is a binary operator. It's kind of like a plus or a minus. So if I wanted to add 2 numbers, I would write like 4 plus 3 and get 7. So I would enter number, then operator, then number. NPR works the same way, the permutation operator. So if I wanted to compute 10p6, I would type in 10, the first number that I'm interested in. Then I would go to my math menu, probability, and option 2 here, NPR. I would insert that operator. It's acting kind of like a plus sign or something like that between 2 numbers. And then I would enter 6. And I see again, I get 151,200. So something that's a little funny is we like actually completed the factorial here to get a formula like this. But if I imagined, say having 100 cities I could visit, or the salesman could visit, and he's only going to choose 6 of them. What's 100 P6? So insert a 0 here. 100 P6, I mean, it's a big number, 8 times 10 to the 11, but it's not, it doesn't overflow the calculator. But what would 100 P6 give me here? This would give me 100 factorial over 94 factorial. If I were to try to do that, if I were to try to do 100, keep forgetting to switch to my calculator. If I were to do 100 factorial divided by, what is it, 94 factorial. Now I know that there's going to be a ton of cancellation here between the numerator and denominator, and that's going to keep the size of the overall answer to a number that's not going to overflow the calculator. But if I try to do this, the calculator overflows. Why is that? Well, because the calculator strategy when I type these things in this way is to say first calculate 100 factorial, then calculate 94 factorial, then divide them. But since I have a huge number over a huge number, it just overflows when it first tries to calculate 100 factorial. The calculator is not quite smart enough to know that, okay, there's going to be a lot of cancellation. I should like do the cancellation first and then see what I get from there. But the programming for the permutation operator, that 100p6 works just fine because that does take into account that cancellation. So the permutation operator will be coded in just as kind of a loop that would multiply over 10, 9, 8, 7, 6, 5. and would avoid those factorials growing too large. So if you're going through a problem and you're getting calculator overflows, ask yourself, okay, am I putting in big factorial numbers? And can I rethink that in terms of, say, a permutation operator, or maybe what we'll see later, a combination operator? So the permutation rule, when we have n distinct items to be allocated to R, a number less than n slots, where order matters, the number of unique outcomes is npr equals n factorial over n minus r factorial. So that's the permutation rule. Now, quick question on this. So npr is n factorial over n minus r factorial. What if r equals n? So what is npn? Well, that's n factorial over n minus n factorial. That's n factorial over 0 factorial. So keep in mind up here, I defined 0 factorial to be 1. So this just makes this n factorial. Is this reasonable? Well, yeah, I think it is, right? If we have n items to be allocated to n slots, that's just the regular salesman problem, right? The regular traveling salesman problem. That's just our factorial rule. So we actually see that our factorial rule is a special case of the permutation rule, where just r equals n, or the permutation rule is a generalization of the factorial rule, where we have fewer slots than number of items. And we can really just kind of wrap the factorial rule into the permutation rule if we wanted to. We could just say allocated to r less than or equal to n slots, and then the factorial rule just kind of becomes part of the permutation rule, just as a special case of it. Okay, so now let's look at a lazy salesman, but now we're in the modern era where all our meetings are over Zoom and such. So now we have a lazy online salesman, a lazy remote salesman. Now this salesman is supposed to meet with 10 different clients. They're only going to meet with 6 of them. But they don't really care about order, right? So if they meet with the client in LA, first, and then in New York second, and then Seattle third, that's no more wasteful or worse than, going LA, Seattle, New York, right? There's really no efficiency or inefficiency to be had with different orderings of different sequences of clients. So I'm going to call these agendas instead of itineraries, suggesting that the order doesn't matter. It's just a question of which clients am I meeting with today. It doesn't really matter which one I meet with first, second, third, because we're remote. So if I have 10 items, 6 slots, order does not matter. How many agendas do I have? Well, one thing I might do is I might just start by saying, well, what if order did matter? Right, I have my 6 slots. Well, if order did matter, my number of agendas would just be 10p6, right? It would just be 10 factorial over 10 minus 6 factorial. But now I say, okay, well, but I want to impose the condition now that order does not matter. What does that do? Well, I could imagine picking an agenda like LA, Cleveland, New York, Seattle, Miami, Wheeling. That might be one itinerary that would be a distinct itinerary under the order matters, under the permutations structure. But if I had, for instance, Cleveland, LA, New York, Seattle, Miami, Wheeling, that would be a different one under the permutation structure. Or LA, New York, Cleveland, Seattle, Miami, Wheeling, right? In other words, there's going to be a bunch of different itineraries that when we impose order does not matter, count as the same agenda. So these are different itineraries. But these ought to be the same agenda. In other words, when I counted up here, 10 factorial over 10 minus 6 factorial, I've overcounted. By how much have I overcounted? I would like to find out how much I've overcounted by and then correct for that. Well, I've overcounted by a factor of the number of different itineraries that I want to wrap under the same agenda. If I look at an itinerary, in this case, I have 6 cities put into 6 slots. How many rearrangements, how many permutations of 6 cities into 6 slots are there that I want to count as the same agenda? Well, I could have put any of these 6 cities in the first slot. I could have put any of the remaining 5, 4, 3, 2, 1 in the next slots. Well, I've overcounted by a factor of 6 factorial. 6 factorial is the number of ways to put these 6 cities into these 6 slots. That's just the factorial rule. So if I leave this formula alone, I get the wrong answer because I've overcounted by a factor of 6 factorial. So I just correct. I divide by 6 factorial. Right? That corrects for the overcounting that I did initially. That respects the fact that there's lots of itineraries from the initial counting that are the same agenda. In fact, for each agenda, there are 6 factorial different itineraries that now map to that single agenda. So I just divide my previous kind of first pass answer by 6 factorial to correct for that. So this structure also has a name. This 10 factorial over 10 minus 6 factorial times 6 factorial is called a combination. Combination. And we say 10C6, or sometimes the C is pronounced choose. So sometimes we would say 10 choose 6, or we might say 10C6. And we can come back over to our calculator to calculate this. 10C6 works just like 10P6. So just like above, we would type 10, and then we go to our math probability menu. But here we go to the third line, and CR combinations. And I see that 10C6 is 210. Right, much smaller number than the, what was it, 151,000 or so that we had up here. Only 210 different agendas for the lazy online salesman. Because there are 6 factorial, that in and of itself is a pretty big number. What is that, 720, something like that? That's a pretty big number of distinct itineraries that map to a single agenda. So that's why our result here is so much smaller than when order mattered. Something else that we might note is that if I had, say, 10C4, well, that's 10 factorial over 10 minus 4 factorial times 4 factorial. But I note that 10C4 should just be the same as 10C6. there's a symmetry here, right? That 4 there and that 4 there. Or that 6 there and that 6 there. So what's another way to think about these combination and permutation rules? Another way to think about combinations is, well, when I say I want to take 10 items and put them into 6 slots, but order does not matter, I can kind of imagine that I have a bag of 10 items. So I have a bag of 10 pieces of paper. Each one has a different city written on it. And I want to pick 6 of them out. Remember, order doesn't matter. So I'm just picking 6 to put into these slots. And then I'm going to leave the remaining ones in this bag also unordered. I could really think of these slots just as like another bag, right? Or maybe I'll use the analogy of a box. So I could really think just putting these 6 into another box where order also doesn't matter. So how many ways are there to pull 6 items out of this bag and put them into another box? In other words, that's just asking how many ways are there to split these 10 items into an unordered group of 6 and an unordered group of 4. Well, that's the same way that we can split it into an unordered group of 4 and an unordered group of 6. So likewise, 10 choose 1 and 10 choose 9 are the same number, or 10 choose 2 and 10 choose 8 are the same number, because they're really asking the same question. How many ways are there to split 10 items into an unordered group of 1 versus an unordered group of 9, or 2 versus 8? Does that mean permutations are share the same symmetry? Well, the answer is no for permutations. We can see that in the formula, but we can also see this kind of practically, that if we have our bag of 10 items up here, and if I pick out 6 of them, well, now it is important that we put them into slots, because the 6 that we pick out, we have to decide which one is going to go first, which one is going to go second, which one is going to go third, fourth, fifth, and sixth. The other 4 are just going to be left unordered in the bag. So the ones that we pick out, we impose an ordering. The ones we leave in the bag, we leave unordered. So we're partitioning these 10 into 6 ordered versus 4 unordered. That's different than having 4 ordered versus 6 unordered, right? We can't swap those. We lose that symmetry. But for combinations, we have this nice symmetry, and we can take advantage of that in some problems in the future. The other thing to note is something like 10 choose 0 is 10 factorial over 10 minus 0 factorial times 0 factorial. This ends up being 10 factorial over 10 factorial times 1, or just 1. If I have a bag of 10 items, how many ways are there to pick out 0 of them? Well, I just leave them all in the bag. That's the only way. And likewise, 10 choose 10. This becomes my 0 factorial. 10 factorial over 10 factorial is 1. If I have 10 items in a bag, and how many ways are there to pick all of them out of the bag and put them all in the box? There's only one. I just have to pick them all out, put them all in the box. So the combination rule says when we have n distinct items be allocated to R less than n slots, where order does not matter, number of unique outcomes is given by this formula. And we can have R equal to 0 or R equal to n. And we see that doesn't really cause any problems, right? By defining 0 factorial as 1, we allow for those edge cases, and that works out just as we would expect. So a quick summary, the fundamental counting rule, we we are in a structure where order matters. And something that we sometimes say is we're choosing with replacement. In other words, when I was all the way, oh, where was I? When I was up here in my license plates, right? I had A through Z items that could go in the first slot. If I pick A for the first slot, it's not like I can't use A in the second or third slot. I replace A back into the pool and I could choose A again. Unlike, say, the traveling salesman, where if I go to LA for the first leg of the trip, I'm not going to go back to LA. Once I've used that, it's gone. I can't reuse it. So the fundamental accounting rule, order matters, choosing with replacement. The rest are choosing without replacement, factorial, permutations, and combinations. Remember that factorial rule and permutations really are kind of the same rule. Factorial is just a special case of the permutations rule, or permutations is a generalization of the factorial rule. The factorial and permutations share that order matters and we're taking without replacement. But the factorial rule has the little criterion that we have the same number of slots and items, which makes the permutations rule a generalization of factorial rule. And combinations, the big difference is that order does not matter with combinations. Still choosing without replacement, but order does not matter. Okay, so that wraps up our discussion on the accounting rules, and that wraps up chapter 4. So again, on Tuesday, we'll start into chapter 5, take a glance through section 5.1, get an idea about discrete probability distributions, and we will pick up there on Tuesday.